Have you ever wondered why your cell phone doesn't have any reception when you're in the middle of a large skyscraper?
Or are you interested in how metals function near magnets and magnetic fields?
Or maybe you're curious about how supercooled superconductors work?
I'm Nick.
And I'm Derya, and we're students of applied physics here at Eindhoven University of Technology.
This is part 1 of a video short in which we're going to explain various kinds of basic physical concepts. This video is all about ferromagnetism and Faraday's law of induction. Welcome to one of the laboratoria in the Department of Physics, the Flux building, here on the Eindhoven University of Technology campus. Well, in order to explain the concept of the Faraday's law of induction and how metals interact in the neighborhood of magnets, ferromagnetism, I'm going to use an experiment. Well, in-house we call this experiment the flying rings experiment. And why this will become apparent in a second. Well, what does this experiment actually consist of? What are all the parts? Well, to start with this is a voltage source that generates the power and the current needed to run the rest of the experiment. So for the rest this is not quite important. On the other side I have a magnetic coil which, if a current is run through it, can create a magnetic field. But right now it doesn't do that, and that's because in the middle I have a button that interrupts the circuit. Well, from the moment I push that button, the circuit is closed and a magnetic field, a current can run through it, creating a magnetic field. Well, the rest of the experiment consists of varying sizes of metal rings. These metal rings do not interact with each other, they are not magnetically charged, they do not attract or repel each other at all. And those rings are all various sizes. For example, I have a ring that's average size, I have one that is thicker than the one I just showed before, I have one that is really small, tiny and not as thick, and I have one that is not enclosed at all. Well, I just told you that nothing happens with these rings. They do not interact with each other and are not magnetically charged. But even more important, they are not attracted or repelled by the setup itself. So right now the ring just lies there. But from the moment I push the button again, the ring flies up. Well, that's weird. We just saw that the rings don't interact and the setup only creates a magnetic field. The rings are not magnetically charged. So, in order to explain this, we're going to need some theory. And that's why we're going to head over to Derya in the lecture room.
So, in the experimental setup that Nick just showed you, we have a coil through which we can run an alternating current, and we have a metal ring. So this metal ring is made up of atoms, like any other object in the universe. Atoms have protons, neutrons, and electrons. Electrons are quite special in our case. They have a certain property called magnetic dipole moment. And here is a little illustration. This is our ring, and it has moments, dipole moments, which are pointing all in different directions. Each dipole moment has its own magnetic field, but it's very tiny and therefore very weak. So when all these dipole moments are pointing in different directions, nothing happens. This metal ring is not electromagnetically charged. But what happens if a metal ring is put in an external magnetic field? Here's what happens. These dipole moments align parallel to the magnetic field and parallel to each other. So all their tiny magnetic fields add up and create a magnetic field of the metal ring. So this metal ring becomes electromagnetically charged if it is in the neighborhood of an external magnetic field. Shortly, this is the concept of ferromagnetism, which tells us how metals behave in the neighborhood of magnetic fields. Now let's go back to our setup. Here we have a coil, and as Nick already explained, from the right-hand rule we know that if we run an alternating current through this coil, the magnetic field will be pointing upwards. Now, if we take a look at the Faraday's law, we can see that a changing magnetic field produces an electromotive force. This electromotive force is proportional to the current. So this changing magnetic field, because of the current, produces a new current. So if we put our ring on top of the coil, a current is going to run through it, if current is running through the coil. This is our ring and the current. And in nature, things want to stay as they are. This also applies to our ring. The magnetic dipole moments want to be aligned in random directions. They don't want to be parallel to each other. So when the current runs through the ring, the magnetic force that is created is pointing in the opposite direction to the magnetic field that is created in the coil. This is the magnetic field from the coil and magnetic field produced by the metal ring. They're pointing in the opposite directions, and therefore the ring and the coil repel each other and the ring jumps up.
So now that we know the theory behind ferromagnetism and Faraday's law of induction, we can do some more experiments. Well, right here I have the very small ring that I told you about and the very large ring. This small ring is much thinner than the ring I used before in my experiment. And this ring, the large thick ring, is much thicker than the ring I used before. Well, once again, I put one of the rings, in this case the very small and thin ring, on the experimental setup again. And then my question to you is, what do you think is going to happen with this ring? Do you think it's going to go higher, lower, or equally as high as the ring I just used before? Think about it for a moment. Well, have you thought about it? Let's press the button. Well, as you can see, it doesn't jump nearly as high. Well, if I put the large ring on it, the very thick ring, it jumps much higher than the ring I used before. Well, why is this? For this, we need some more theory.
So, why did the thinner ring jump lower and thicker ring jump higher? Let's compare the rings to a wire which can conduct electricity, as drawn here. This wire has a length L and a cross-sectional area A. From the equation over here we can see that resistance is inversely proportional to the cross-sectional area. What does this mean? This means that the smaller the area of the wire, the higher the resistance, and the other way around. The larger the area of the wire, the lower the resistance. From the equation over here, we see that the current is inversely, again, proportional to the resistance. If we combine these two equations, we can get this relationship. Area is proportional to the current. So the smaller the area, the smaller the current can run through the wire, and the higher the area, the higher the current. This goes not only for wires, but also for our rings. So the thinner we have the ring, the smaller the current, and therefore it can create only a smaller magnetic field. So the magnetic field through the coil is opposed by a weaker magnetic field through the ring, and therefore the repulsion is smaller and it jumps lower. Same goes for the thicker ring. The magnetic field is stronger, the repulsion is stronger, and it jumps higher. But what happens if this ring that we have is not complete and it has a hole in the middle? Well, we can think of it as of a circuit. If a circuit is not complete, current can't run through it. If our ring is not complete, current cannot run through it as well, and therefore no magnetic field can be created, and thus it's not going to jump up at all. Let's test this theory in the lab with Nick.
Well, great theory, Derya. Let's put it to the test. Well, right here I have a ring with a slit in it, so it's not entirely closed. As we would expect by the theory, because the ring is not closed, a current is unable to run through the ring, and because a current is unable to run through the ring, it can't create a magnetic field in the opposing direction, so it won't repel and won't jump. Well, let's put the ring around the experimental setup and press the button. But as you can see, I can press the button as many times as I would like, but nothing happens. So once again, our theory coincides with our observations. So for the last part of our experiment, I've put on some safety equipment, some special gloves and some special goggles as well. And that's because I'm going to be working with liquid nitrogen. Well, I've super cooled the ring that I first used in our first experiment, and I've cooled it down to minus 200 degrees Celsius, the temperature of liquid nitrogen. Well, in a moment I'm going to put this ring right over here on the experimental setup again and make it jump. But my last question to you is, how high do you think this ring is going to jump? Is it going to jump higher, equally as high, or lower than the first ring I used in the experiment? And remember, this ring is exactly the same as the ring I've used before. So, while you're thinking, I'm going to put this ring on the experiment and then make it jump. And as you guys saw, it jumped way higher than the first ring did in that experiment. And that's because of the following. Metals, the resistance of metal depends on the temperature that that metal has. And usually it's the case that if a metal gets hotter and hotter, the resistance of it increases as well. And that's why in the old light bulbs, the light bulbs will glow, because the resistance is so much and the temperature is so much as well that it produces a glow. Well, this is the exact opposite. Because the ring is so cool, the resistance of it is very low. And because this resistance is very low, a much higher current can run through it. And because a much higher current can run through it, a much larger magnetic field is created. And this much larger magnetic field repels from the other magnetic field, and that's why it jumps much, much higher.
So what have we learned in this video?
Well, we have learned that if we expose a metal to a magnetic field, it becomes electromagnetically charged. But not only that, we have learned about Faraday's law, and that by introducing a varying magnetic field, we produce a current.
Apart from that, we have seen how scientific theory can explain what we observe in real life, and also how this scientific theory can be proven by experiments.
If you like this video and would like to know more about studying physics here at Eindhoven University of Technology, go visit our website down below.